Okay, so exciting times. Are you guys ready to find the volume of surface of revolution? So, so this is the basic idea. So let's start off with the basic idea. So let's say you start with a region, so like an area. So for example, just to give you kind of an example, suppose we have the area under square root of x from 0 to 4, just to pick something simple to illustrate the idea. So if we look at this area, so square root of x, the function, looks like this, right? Here, this is 4. What's the y value there? 2, right? Okay. So this is an example of just, it's the square root of x, but the idea works with any function. So you have this area here. So this is my region. So the area under square root of x. Okay, so imagine there's magic. Okay, magic, like, you know how they're nowadays, so see, you guys are lucky because you guys can visualize this in real life. You guys have now 3D printers. Have you guys ever seen a 3D printer? Yeah. I have never, but I hear that they're a thing. Okay, so you imagine that this is kind of like a 3D printer. Okay, so imagine you have this, imagine this is a sheet right here, right? Okay, now, you take this sheet in this shape, whatever it is, right? So you have this shape. And imagine you rotate it, let's say about the x-axis, and as you rotate it, it's creating a solid. Imagine it's printing wherever it goes. So like this sheet rotates around. So what you end up with is yeah, I mean kind of like a cone head. Do you guys seen that movie? Cone heads. So this is like a 3D cone head type of a deal, right? Okay, so you end up with a solid. Now, this solid, notice what kind of a base does it have? Well, it's not elliptical, it's a circle, right? Because so this is the tip right here, right? So imagine that tip goes around. What's the radius of that outer edge? Always going to be 2, right? The radius is always going to be 2. From the center to that edge, that's always going to be 2 because that's what's going around printing your solid, right? Does that make sense? Okay, so if you want a computer-generated version, see, you guys are also lucky. We did not have this back in the day when I took this class. But Wolfram, even just a couple years ago actually, Wolfram could not do this. But now if you tell it, for example, rotate the region between 0 and square root of x from 0 to 4 about the x-axis. It understands that. So it gives you all this weird stuff, but then it gives you the picture. So that's what it looks like. Is that what you guys visualized? Yeah. Kind of, sort of, maybe? And you can do show solid here, and it'll show you something that... Now, they won't let you move it around unless you pay money. And
pay the money, it's worth it. I pay the money. Just do it. Usually just do it.
Say you're in school, it's $2. You can get the student discounts for that.
Yeah.
Well, I don't need it. But, see, it won't even show me the solid. Look at that. Still thinking. That's the one thing I don't like. It's too slow.
You're also on school Wi-Fi, so.
Well, okay. Anyways, so that's what it looks like. Okay, so what we want to figure out is how do we find the volume of this solid. It looks hollow now, but imagine it's solid, because I clicked this button here and it was gonna fill it out for you, but then it's taking too long. So, okay, but this one's filled out. Okay, so you will be surprised to find out that the strategy is very similar to the strategy we use to find the area under the curve. We just apply it a little bit differently. So you remember, what was the strategy we used when we were trying to find the area under the curve? What did we do? Well, no, that was the end. That was at the very end. How did we start off finding the area under the curve? Yes. Well, we broke it up into subsections, right? And then we added those up. Okay. So the strategy is similar. So let's say you split this into subsections here. Now, you don't necessarily have to, try to draw. I'm already going to do a bad job as it is. So, but imagine you break this up. Okay? So here I drew, I don't know, what is that? 1, 2, 3, 4, 5, 6, 7, 8 sections in this case. Okay, so we break this up. So if we take a look at just one of these, let's say this one right here. Okay, so imagine you cut it up and so you slice it down. Imagine you get a sharp knife and you slice it. What do you see when you look at the face of it? What shape? You see a circle, right? So this right here is the same as the bottom. It's a circle. So here, let me do an arrow here. Okay, so this right here, if I look at it straight on, it looks like a circle, right? Okay, now, question. So the idea is, well, actually, let me do this. Hold on. Let me do a little bit sideways first. Okay, so I'm going to do, so it's a circle, but I want to do a three-dimensional version. So this is what we call, well, it's a cylinder basically, right? But we call it a disc. So this is a disc. Okay, now, a couple of key things here. So to find the volume of this disc, we need, it's just a cylinder, right? So all we need is the radius and the height, right? You guys agree? Okay, so so like right here, well, okay, let's do the height. The height is easy. So what is the height right there? The height of the cylinder. That's going to be delta x, exactly. So notice this is delta x down here. So that's just the width of your subsections. And just like we did when we found the area under the curve, here I have 8 subsections, so delta x is pretty big. But what are we going to do? We're going to make the number of subsections eventually go to infinity, right? And so then delta x is going to shrink down to, yeah, it's going to go to 0, right? Okay. All right, now, what else do we need? The radius. What's the deal with the radius there? It would be smaller than what? Smaller than 2. That is correct. In this case, sure, it would be smaller than 2. So let's draw where the radius is over here. So if I'm looking at this subsection, the radius is basically that distance right there. Do you guys agree? So that's the radius right here. And what is it going to be? Well, notice it's changing, right? So it depends on where you are. So how would I write that then? In this case, it's going to be, isn't it just the f of, depending on what x value I'm at, right? So the radius is f of x sub, so let's do, because we're going to add up all the discs. So let's call this the ith disk, because we used I. So this is this is going to be f of x sub I, where x sub I is just the x value that we're at. So this would be f of x sub I. All right, so now, what would be the volume of the ith disk? So it's just a cylinder, right? So what's the volume of a cylinder? Almost. Pi r squared, which is the area of the base, right, times the height. So our cylinder is sideways, but it's basically, so pi, right, r squared times the height, right? So what is that? If I translate it, that's going to be pi. The value of the function in this case, right? F of x sub I delta x. Yeah, let me well, okay. Pi f of x sub I squared delta x. Okay, so that's one subsection. Yes? All right, so let's go down here. So do you guys agree then that the volume is approximately equal to the sum of those disks? So in this case, I have how many? In my picture, I have 8, right? So I'll just say from 1 up to n. But so in this case, I drew 8. If we want it to be more accurate, we could use 10 or 100 or 1,000 or 1,000,000, right? Okay. So what is this equal to? If I expand this, this would equal to the sum from 1 to n of pi f of x sub I squared delta x. Okay, now this is the question. Always when we're trying to, because obviously, so we've already been through this once before in a way. If we're going to let n go to infinity, do we enjoy evaluating that directly? Absolutely not, right? We do not like doing that. So our goal is we basically ask ourselves, okay, hey, is this right here, question mark, is this a Riemann sum? Why do we ask ourselves this question? So this is a really important question. So if it's a Riemann sum, that means that when you let n go to infinity, you can turn it into an integral, which makes it easy to evaluate. If it is not a Riemann sum, which you'll see in Calc 2 sum and in more in Calc 3, then you have to do some shenanigans to try to turn it into a Riemann sum. But the idea is always the same. Is you take your problem, notice, so because you're going to see this pattern a lot. You take your problem. What is our problem? Find the volume of this solid. Okay. Well, let me use calculus to answer this question. So what do? Well, I chop it up into pieces. In this case, 8 pieces. And then I find a formula to approximate that volume using these pieces. And then I let the number of pieces go to infinity. And that sum, if it's a Riemann sum, I can turn it into an integral and easily evaluate it. If it's not a Riemann sum, well then either I'm out of luck or I have to do some other stuff to turn it into a Riemann sum. Does that make sense? Okay, so this same exact strategy you'll see repeated over and over in different contexts, but it's the same strategy over and over again. Okay, so I've been throwing around Riemann, but you guys maybe don't quite remember what it means to be a Riemann sum. Do you guys remember? Okay, so let me let's see. Let's go open up a new sheet here so that we can write down. So for us, Riemann sum. So let's recall the definition of the integral. So I know it's been a while. Well, the definite integral. So we had this. The integral from a to b of f of x dx. So this represents the area underneath f of x from a to b, right? So we said this is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x, right? Okay. So this right here, so this is an example of a Riemann sum. So the key things that you need to have is you basically have to have some function, so function, and then delta x. So you have to have that pattern. So the function can be any function, but it has to be function value times delta x. So I mean, it could be a function of y and delta y. That's fine, but it has to have that pattern. So if I compare this sum right here to the one that I have over here, does that look the same, or does it have the same pattern? Sure, it does, right? You have pi is just a constant, so you can take it out of the sum. It's no big deal. You have f of x sub I squared. Well, it's just a function, and it's squared. Well, it's still a function, right? And then the other thing is it's multiplied by delta x, so you're good to go. Does that make sense? So, so then this is, the answer to this is yes, and this gives us a smile. And so then we say, okay, onward march we go. So, okay, so then let's use it. Let's write it down over here. So from the previous page, we had the volume is approximately equal to the sum from I equals 1 to n of pi f of x of I squared delta x. So then we say, okay, well, let n go to infinity. Then what happens to delta x? It's going to go to 0, right? So we have that the volume is exactly equal to the limit as n goes to infinity of the sum that I just wrote down, right? And since it's a Riemann sum, this is equal to the integral of what? Well, I'm going to have pi, right? And what am I going to have inside the integral? I'm going to have f of x squared and then dx, right? And then from where to where? Well, it's going to be from a to b, which is wherever we're finding the volume. So these are the x values in this case. So notice we did this with respect to x. The idea is exactly the same with respect to y. Okay, so does that make sense? Yes? All right, so now, so any questions about that? Because I want to go back to the picture real quick. So the way you want to kind of look at this is, so the strategy, so this is a simple example, but later in a little bit we're going to also do examples where there's like, oh, the area is between two functions and whatnot. But the idea is always the same, and the idea is that you take a slice here. So you take a slice, and you find the volume of that slice, that piece that you found. So what's the piece in this case? It's a disk, right? And the volume of that disk, well, it's a cylinder, so it's whatever it is. In this case, pi r squared times h. So this is the volume of that section. And then you take that and then you add them infinitely many of those from in this case, from 0 to 4, right? From x equals 0 to x equals 4. So the way you kind of want to imagine it is it's like you're starting at 0 and 4, and you're scanning through from, in this case, the left endpoint to the right endpoint. As you're scanning through, you're collecting the volume as you go. It's like infinitely many little pieces, and you're collecting the volume as you go from one end to the other. Just like when we found the area under the curve, it was kind of the same idea. You're collecting the area as you go from one end to the other. Here, collecting the volume from one end to the other. Yes? Okay, all right, so let's find the actual volume for this guy then. So, okay, so, all right, so what do we need? So, we need, well, should I draw it again? I guess I should. I'll draw a quick picture so that we kind of have it right here. So this is, okay, so this is what you want to do. So this is the region, right? And you rotate it, and then this is your kind of your picture. So a really important piece is, so you have the cross section is a circle. What I like to do is I like to take the cross section and put it as if I was looking straight at it. And you can go back and forth between the picture and the cross section to make sure that you have the right quantities. So here, for example, what I need to know is the radius, right? I need to know what the radius is. So the radius is that right there, right? So what is that? It's the square root of x sub I, right? Square root of x sub I. So the function is square root of x. So the length of this line is square root of x sub I. Does that make sense? Yeah? Okay, and then I don't worry about the width because that's just delta x, right? So what you so in this case, it's for the next few ones, they're all going to be circles, but we're also going to look at different shapes of cross sections. So the main thing you want is you want to figure out, okay, well, what's the formula for the area of the cross section? So it's good to get used to doing it that way from now, starting now, because as we go forward, then we'll have different shapes, so it'll be easier for you to make the transition. So the area of the cross section is equal to, so in this case it's a circle, so it's pi r squared, right? So in this case, what would that be? That would be pi, well, r squared, so pi times square root of x sub I squared, so pi times x sub I. And that's it. Yes? So far so good? Okay, and then the volume is basically just the area of the cross section times the delta x, right? Does that make sense? Okay, so then the volume is equal to the limit as n goes to infinity of the sum from I equals 1 to n of basically this guy right here. So what is that going to be? That's pi times x sub I delta x. Does that make sense? So see how this guy right here, so the pi is there, right? This x sub I, what is that? That is, yeah, that's the f of x sub I squared that we had earlier, right? Okay, so then the whole point of this is to then turn it into an integral. So this is equal to the integral from where to where? 0 to 4, right? So from x equals 0 to x equals 4 of pi x dx, which is just what that sum infinite sum equals, right? And then this is no big deal to integrate. This is pi x squared over 2 from 0 to 4, right? So what is that? 8 pi. So that's the volume of that solid. Okay, so I kind of over-explained what we needed for this specific problem, but only because I wanted to give you guys a more general strategy that'll work with all different kinds of shapes. So this is really important, this area of the cross-section. So you always, what you do is you take a slice and look at the cross-section. What is it? And then find the area of that cross-section. And what's the volume of that cross-section? Well, it's just the area times delta x or delta y, depending on how you're slicing it. And then you turn it into a sum, and then from the sum you turn it into an integral, and then you evaluate it, and you're done. Yeah? Okay, all right, so let's do another one. Any questions before we do another one?
Quick question.
Yes.
Is that an exact area or an approximate?
It's an exact area. The exact area. Exact. Cannot get more exact. Okay, all right. You guys ready? So find the volume. Find the volume of the solid. When rotating the region between let's see, x equals square root of y and x equals y over 4. We're going to do two problems actually, about the x-axis and about the y-axis. All right, so what do we do first?
Draw a picture.
That's right. That's exactly right. Draw a picture. So let's see here. So x equals y, square root of y. What does that look like? Half of a parabola, right? The right half. So this is x equals square root of y. And then x equals y over 4. What does that look like? Okay. Okay, so what is this? We're probably going to need to find this intersection point, right? So what is that? Where does square root of y equal to y over 4? What is it? So you can set them equal to each other, right? But it's, so when x equals 4, y equals 16, that's where they intersect, right? Okay, so all right, so we're going to do part A first. So this is the region, right? The area between those two guys. And so now if I'm going to rotate it about the x-axis. So we're going to do part A here. So all right, so now what does this look like? So what I would do is whatever you're rotating it about, treat it like a mirror image. And so pretend this is the x-axis is a mirror, and then just reflect. So this point here, which is 4/16, if I reflect it across, it would be 4 minus 16. So, and then, so I'll draw a straight line here like that, right? And then looks kind of like that, right? Okay, and then it kind of depends on how much. Well, it depends a lot on your artistic ability. Now, I will admit that mine is quite poor. Now, thankfully, you don't need to have good artistic ability to answer the math problem, but it does help to have a pretty good idea of roughly what it looks like. The most important part is actually the area of the region. So if you don't have the region right, then you'll probably get it wrong. But if you at least have the region right, then that's most of what you need. Okay, now let me ask you a question. If I take a slice, so right here, wabamo, I slice it. What is it going to look like? It's going to look like a donut. That's right. It's got a hole in it. Do you guys see that? It's got a hole in it because there's this region right here that doesn't have a solid in it. Right? So if I look at that red circle that I drew there, it's going to look like that. Where only this has the outer part has the solid in it. Does that make sense? Okay. So the important thing to realize, though, is the strategy is still the same. It doesn't matter if you read a calculus textbook, they always try to split it up into all these different cases. It's really simple. There's only really one important idea. It's you want to know what's the area of that cross section. So if the cross section changes, well, then you just figure out the area of the cross section. So, if I want to know the area of this, the shaded area, what would I do? Subtract the big area minus the small area, right? I mean, it's not very complicated, right? Okay, so, all right, so the area, so let's write this down. So the area of the cross section is equal to the area of the big minus the area of the small. All right, so that's pretty straightforward. That doesn't take too much brain power to figure out. Okay, so now what you need to do is you need to figure out, well, it's a circle, right? So you need to figure out what's the area of, well, basically you need the radiuses, right? The radius of the big and the radius of the small. So this is, I'm just going to call this R small and R big. Okay, so here's a big tip. Okay, you guys ready for the big tip? It's very important when you're looking for your radius. Always, always, always. So you draw the radius, right? So here's the center. And then you kind of have the option of drawing the line up here, or you can draw it down here, right? Do you guys see that? You can draw it from the center. You can either draw it up or draw it down. Did you guys miss that? So see how the green line, this green line that I drew over here is this green line right there, right? It's kind of hard to see, but okay, but you can also draw a green line to the bottom. That's the same radius, right? Whether you go to the top or you go to the bottom. Okay. Always, 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 always draw it to the original region. Okay, so which one's my original region? The one on top. Always do that. Always. No matter what. Why? Because if you don't, you're going to get all mixed up and confused, and you're going to end up doing it wrong. Okay, so if I do that, also very important to know, what are you going to be integrating with respect to? Well, it depends on what part you're talking about. So it's also not difficult to know. All you need to do is think about whether when you slice it, is your thickness a delta x or a delta y? So like notice I slice it vertically like this, right? So my slice is standing up. If I give it a little thickness here, it would look like that, right? You guys see that? What is that, delta x or delta y? That's delta x, right? So that tells you you're going to be integrating with respect to x. The other way that you might want to think about it is, so think of it like the scanning example that I was telling you, that as you scan through, you're collecting the volume. What do you go along to collect your volume? You're going to go along the x-axis, right? Like if you imagine your little discs here are collecting volume as you go. Your discs are standing up and you're going left to right. You're going along the x-axis. So that means you're going to integrate with respect to x. Yes? Okay. All right, good. So, all right. So that's important because I'm going to write it down right here. Integrate with respect to x. It's important because whatever you're integrating with respect to, that's what you want to write your function down as in terms of that variable. So if I'm going to integrate with respect to x, it doesn't matter how I'm given the functions. I need to make sure that I have them with respect to whatever I'm going to integrate, because you can't have mixed variables. It doesn't make any sense. Okay, so what's the length of that green line that I drew right there? So this green line right here, that right there. Nope. Well, okay. Okay, do you guys see the problem with that? So this is the problem, is that it's not wrong, but it is wrong. Do you guys see what I mean? What did I just say? It needs to be with respect to x, right? What I'm looking at here is I want to know what is the length of this line, right? Well, this is a y value, right? So, yeah, exactly, 4x, yep. So, that radius, the length of this line is the y value at that x value, which is, so it's going to be 4x. Does that make sense? Okay, now, let's see here. So what about the small radius? So that's this right here. All right, what is that? There we go. That's the spirit. X squared, right? Because again, notice, what are you looking at? You're looking at the vertical distance, right? What is that? That's a y value, right? So it's whatever y equals to, which is x squared.
So basically we're just solving for x. Solving for y.
Yes. But all the pieces need to be in place. See, this has to be decided first. What are you integrating with respect to? Once you decide what you're integrating with respect to, then you can see if you're going to need to solve for anything. Does that make sense? Okay. All right. All right, so let me erase that so that we have a little bit more room here. Okay, so we said, all right, so let's write down the area of the cross section we said was area of the big minus area of the small, right? And we said what that was. So it's going to be, what's the area of the big? Pi times 4x quantity squared, right? Okay, minus area of the small, what is that? Pi times x squared squared, right? Where did the 4x and the x squared come from? From the big and small radius that I found earlier, right? Okay, well, so what is that equal to? That's pi times, what is that? 16x squared minus x to the fourth, right? If I just factor out the pi. Okay, so then, all right, so that's the area of the cross section. So then, what's the volume going to equal to? The limit as n goes to infinity, right, of the sum from I equals 1 to n of, so what's going to go in here, inside of the sum? Yeah, the area of the cross section, basically, right? So this right here, this area of the cross section is going to go in that spot, right? Because how do I get the volume? I take that area and just multiply it by delta x, or delta y if it's flipped. But it's just pi times 16x squared minus x to the fourth. And what does that equal to as an integral? It's going to be pi times the integral from well, I'll put the 16x squared minus x to the fourth dx. Actually, I forgot the x. These should be x sub I, right? Because we're still adding them up. But inside the integral, so from where to where am I integrating? Okay, so this is really important. Am I looking at are the limits of integration going to be x values or y values? X values, exactly. How do I know that? Because we're integrating with respect to x, right? So x values, so from where to where, basically just look at from where to where is your area, the region that you rotated. Well, it was from 0 to 4, exactly. And then whatever that is, I don't know. But you guys know how to integrate that, right? So integrating is not the hard part. The hard part, obviously, is setting it up. Okay. So what do you think about that? A little bit more involved, right? It's going to take some practice. Do you guys want to do it about the y-axis? Sure. Okay. Great. Let's see. All right. Any questions about that one? Okay. So you guys get to finish it off and do that. And you can always check it with Wolfram if you want. Okay. So the same problem, right? Just so we have x equals square root of y. X equals y over 4. But this time we're going to do it about the y-axis. So what does that look like? So exactly the same picture here.
Symmetry going to be the other way?
Yeah, so notice we're going to rotate it about the y-axis like that. Okay, so now what do? So we do the same thing. We're going to draw the picture. We're going to reflect across the other side. So, you know, you just kind of try to do a good job. And it doesn't have to be amazing by any stretch of the imagination. So what does that look like? What does the solid look like? What would you say? What do you think? So like if you're looking at it straight, like if you're bird's eye view and you're looking down, what does it look like? It's like an inverted cone, right? So it's like a cone on the inside with funny tips. So it's like a bowl, but a cone bowl. But it's round on the outside, right? So strange bowl. Not very good for eating, but maybe for something. I don't know. Okay, so, all right. Can you guys tell me what I need to do? So what's the strategy? What do I do first? So I drew this picture, right? Yep, draw a cross section. So you take a slice. Now notice, though. So imagine this. Okay, so you guys imagine the funny bowl in your head, right? Okay, now. Okay, so don't draw this, but you slice it this way. What is it? If you look at the cross section, what is it going to look like? No, it's this way. So imagine you have this bowl, right? So imagine a bowl. Rounded on the outside, right? But it's a cone on the inside, and then you just slice it, but vertically. It doesn't look like a shape that you know, right? It would, or even just imagine a regular bowl, and if you take a regular bowl and you cut it vertically and then you look at it, what does it look like? Well, it just looks like this weird U type of a thing, right? But it's definitely not a geometric shape that you know how to find the area of, right? So the reason why is because that's not how you're supposed to slice it. So notice, because we rotated it about the y-axis, we should slice it horizontally instead. Does that make sense? You guys see that? So if you ever kind of encounter that issue where you're like, well, I don't know what the cross section looks like. Well, maybe you sliced it the wrong way. So notice if I slice it this way now, what does it look like? Yeah, it's a circle, right? Similar to it's still got a hole, right? But it's a circle like the one we just did. Like that. So that looks like this. And so okay. All right. So again, the strategy is the same. We have this R big, right? The big radius, the small radius, which maybe I should probably go down here. Small radius. Okay. So, all right. So now, again, before we do anything, what are we going to integrate with respect to? We're going to integrate with respect to y. How do I know that? Well, look at your slice, right? What is it? If you imagine kind of scanning through and collecting the volume, notice you're going to have to go vertically up the y-axis, right? You guys see that? So that tells you we're going to be integrating with respect to y. And so, okay, so that's good. So now, so if I draw this big radius here, so maybe something like that, right? So what is that? What's the length of that line? Shouldn't you go the other way? Exactly. Do you guys see how that could potentially be confusing? It's not wrong, it's just confusing. Because the function that I drew, x equals square root of y, is this one on the right side, right? As soon as you kind of start going to the reflection, then your brain, it's not wrong, again, it's just your brain starts getting confused, like, well, what is this? I don't know. And then you just lose it. You start writing down whatever comes to mind. So you want to avoid that if possible. Okay, so let me go back here. Okay, so this is what I'm looking at, right? So this length right there. So what is that? Well, that's this. That corresponds to this function, right? X equals square root of y. But what you want to look at really is just the length of that line, right? So what is it? The length of that line is the x value, right? Which is square root of y, right? Okay, good. All right. And then, let's see here. What about the small radius? So the small radius is this distance from here to here. And notice that's on the other function, right? It's on x equals y over 4. So what's the length of that purple line that I drew there? It's just y over 4. Does that make sense? Okay, good. So what comes next? What should I write down?
The area of the cross section.
Okay, that's a good strategy. So the area of the cross section is going to be area of the big minus area of the small. Yes? So what is that? That's going to be pi times square root of y, quantity squared, right? Which is just going to be y, minus y over 4 quantity squared. So this is pi y minus y squared over 16. So then, so what's the volume? It's the limit. So don't skip this part. I'm going to ask you for this part. But it's important because you need to know how to go from the sum to the integral, because that's how you actually use it. And if you start skipping the sum step, well, then you'll forget it, and then you won't be able to use it, and then you'll be perpetually confused, which is not good. Okay, so even though it seems like a pointless exercise to write down the sum, I want to make you do it anyways. Okay, so what goes in the sum? All right, what do I put in there? It's the area of the cross section, right? Which in this case is pi y minus y squared over 16.
Checking. Here's what I found on the web for the theory of the cross section. Right?
You guys hear that?
This case is pi y minus.
This Siri just all of a sudden decided to. Here's what I found on the web for the theory of the cross section, right, which is in this case pi y minus. Have a look. That's what it said. Thank you, Siri. I tell you this. I think it was this morning. Oh, I had a Siri annoying moment. Trying to tell her to give me directions to a spot, and then it was so annoying. Okay, so I tell it. I say, "Oh, this place. It was a bank." So then, there's a. I think it was a Union Bank. There's a Union Bank right here on the corner of blah, blah, blah. So then I'm like, she says, would you like me to call or give you directions? And then I said, give me directions. And then she said, I found 10 locations for Todd and blah, blah, blah near you. Would you like me to call the first one? I'm like, no, we were on the bank. I thought you were going to give me directions to a bank. Now you're talking about something completely different. And I couldn't go back. There's no way. So then I just got upset. Because it's kind of like this moment. Except, yeah. Anyways, Siri. Siri. Still got some work to do there. Okay. Anyways, back to the volume. What is this? As an integral, what is it going to be? The integral of, I forgot my little eyes here. Okay, so pi times y minus y squared over 16, right? dy. And then from where to where?
0 to 16.
Yep. From y equals 0 to y equals 16. Right? Because now we go from the very bottom to the very top.
It's still delta x.
Nope. It is not. That was just a bit of a mishap there. Siri's fault, obviously. And then whatever that is, you guys can figure it out. Does that make sense? Any questions? Okay, I'm going to give you guys a little challenge. You ready? Okay, so same region. Same region as this one, but rotate it about the line x equals to 6. Okay, so let's talk about this a little bit, just because, well, so it's similar to the last one, right? So if I look at a cross section, so we're going to slice it horizontally again. So it kind of looks like that, right? So if I take that cross section and I look at it, I can draw it like that, I guess. That'd probably be good. Okay, so it has a big hole in the middle for most of it. But one of the big things, you have to be extra careful with the radius. Because if I look at, so we have the same kind of deal. So we're going to integrate with respect to y again, just like we did in the previous one, right? Because we're rotating it about a vertical line. Does that make sense? That we're going to integrate with respect to y? Okay. So here, notice here's the center, right? Okay, so if I'm going to draw that green line that I just drew, if I'm going to draw it on my graph, should I draw it from the center to the left edge or the center to the right edge? Okay, I heard both. The left, because that's the original function. Exactly. Okay? If you do it to the right, forget it. Might as well just give up and do a different problem. Because you probably will just get confused. So you want to go to the left edge. So this is what you're looking at, right? Okay. So again, you're looking for the length of that. So this is really important. This function, the one that it touches, the green line touches this function right here, right? Which is the function x equals y over 4, right? But you're not looking for the value of the function. You're looking for the length of that line, the green line, because the length of the green line is the actual radius, right? Okay, so what you want to look at it as is think, okay, so this point here corresponds to this x value here and this y value here, right? But the x value, notice this right here, so the value of the function is that length that I drew right here, this black length, that right there. Yes? Okay, so what's the length of the green line? 6 minus, exactly. So 6 minus the black line, which is x. Right? You with me? The length of that green line is 6 minus x, where x is this x value here, the length of that line right there. Yeah? But again, I don't want it in terms of x, I want it in terms of y. So it should be 6 minus, very important that it's this x that corresponds to this function here, which is y over 4. Do you guys see how we got to that point? So that's the big radius. So r big is 6 minus y over 4. All right, so now what about the small radius? Which is this from here to here. So it's probably not hard to figure out now that we figured out that one, right? It's going to be 6 minus Square root of y, exactly. 6 minus that x value, which is the square root of y. Does that make sense? And then everything else is the same, right? So you have area of the cross section is pi times 6 minus y over 4 squared minus 6 minus square root of y quantity squared, right? So that's big minus small. Don't forget to square each of them. So then the volume is equal to the limit as n goes to infinity of the sum I equals 1 to n of all that stuff delta what? Y, right? So it's going to be, well, I'll put the pi on the outside. So I feel like I'm going to need the space here. So it's going to be 6 minus y sub I over 4 squared minus 6 minus square root of y sub I squared. Okay, now that is equal to the integral. Pi times the integral of 6 minus y over 4 quantity squared minus 6 minus square root of y squared dy. And then from where to where? 0 to y equals 0 to y equals to 16. From the very bottom to the very top, right? The y values. And then you evaluate that and you get whatever you get. But does that make sense? Yeah? So like the other stuff, it it takes practice for sure. Because it's a little weird, and try to work on it sooner rather than later. You can get started on the videos. It'd be a good start. Okay.